All right, let's do some E&M. So we're going to start just by introducing the concept of electric charge and show how that can be used in a circuit. So all of E&M is based on this concept of electric charge, which is denoted by either a capital or lowercase q, and this is just a property of matter like mass. So we just will accept that there's this quantity called charge that particles have. And the main governing rule for charges is that there's two types, which we have called arbitrarily positive and negative. And they're governed by the fact that like charges repel and opposite charges attract. So we see that plus and plus push away from each other, minus and minus push away, whereas plus and minus are going to attract. And we say that charge is quantized, meaning you can only have multiples of this elementary charge called lowercase e. And again, we call it lowercase e because it's also the electron charge. So protons carry one positive elementary charge unit, and electrons carry one negative charge unit. So it is actually possible to have things that are less than one elementary charge unit, because if you actually go deeper into a different model of particles, you'll see their protons, for example, are comprised of quarks, and they can have these fractional charges. But these don't exist freely in nature, so we're going to continue to say the lowest amount of charge you can have is plus or minus one electron charge. So to actually measure charge, it's usually inconvenient to talk about in terms of the elementary charge because it's so small. We usually aren't talking about singular electrons or protons, so we define the coulomb, which is a capital C. And the elementary charge has a value of 1.6 times 10 to the negative 19th of these coulombs. So we'll never really see charge that reaches the Coulomb scale for single particles. In practice, we're usually looking at microcoulombs, which is 10 to the minus 6, or nano, which is 10 to the minus 9. So just to practice our charge definitions here, we're going to start with a common example called an alpha particle, which is a helium-4 nucleus, meaning it has two protons, because helium has two protons, and it also is bound together with these two neutrons, which are electrically neutral. So first we want to calculate the net charge of the alpha particle in coulombs. So it's just a nucleus, so we can assume it's just these two positive charges. So we can pretty easily say that our net charge, well, I have two extra positive charge units, and the elementary charge, we actually do want it in coulombs, so we're going to use 1.6 times 10 to the minus 19th coulombs, and doubling 1.6 just gets us 3.2. So you can see that that is quite small. All right, so just to see the scale of this, the scale of the coulomb, how many of these alpha particles would be required to get to 1 coulomb of charge? Well, this is more of a unit conversion problem. So we know that there are 3.2 times 10 to the negative 19th coulombs per 1 alpha particle. That's what we're given. That's what we found last time. So if we actually want to generate 1 coulomb of charge, what we should do is we can set up this relation that I have 1 coulomb that I'm trying to make. And for every particle, so for every 1 particle, there are 3.2 times 10 to the minus 19 coulombs. We can see that we've effectively canceled our coulombs here, and we're going to be left with particles. And if we do this, we get roughly 3 times 10 to the 18th particles. So that's quite a lot. I can't even think off the top of my head what number that is. It's probably in the quadrillions or quintillions at this point. 10 to the 18th. Uh, so would it be likely to encounter this many alpha particles in one location? What do we think? Well, first of all, 3 times 10 to the 18th particles is a lot. But also realize they're positively charged. And we just said up here, positive charges repel. So it seems very unlikely that you have somehow convinced all of these repulsive uh, repulsive particles to be next to each other. So I would say no. Since the alpha particles are positively charged, they're going to repel each other. So they're not just going to agree to be in one location. This is why we have gravity as sort of the dominant force at big scales in the universe, because at big scales, charges are going to cancel out. So we wouldn't expect all these particles to be lumped up together. So instead of talking about individual charges with circuits, usually we're going to talk about the rate at which charge passes through an area, and we call that the current. So think of current as a flow. It's a rate of flow of charge carriers. We'll deal with the direction next time, but we're going to say that the current is defined as the amount of charge, Q, passing through an area in time t. And this is an average current. Of course, you can imagine if we want some sort of instantaneous current, we can do some calculus and change my deltas into D's. So if we look at our units, the Q is going to be measured in coulombs, and T is going to be measured in seconds. So we get coulombs per second is going to be this SI unit of current. And we have a special name for that is an ampere, or an amp. So now we have a fully charged battery connected to a resistor. And after 1 minute, 16 coulombs of charge has passed through. So after 1 minute, which is 60 seconds, 16 coulombs of charge has passed through a resistor. So what is the average current? Well, this is just application of the formula. Definition of current is the amount of Q passing through an area in time t. So we have 16 coulombs of charge that pass through over 1 minute. So we get 0.267 coulombs per second, which is defined as an amp. So not even 2 problems in, and we already have our first 6-7 of the year. Lovely. Also, notice that this is a reasonable number to work with. It's just one number after the decimal. So even though we said that single particles have very small charges in terms of coulombs, there's going to be so many charges that pass through an area in a given time that it balances it out and gives us amps that are usually on the order of single-digit currents. And we'll see that here, because if we actually work out the number of electrons that pass through, and that is a fact we'll also talk about later, that in these circuits, it's usually the electrons that are carrying the charge. So there's 16 coulombs of charge that pass through in this time. Well, how convenient, because we actually know that every electron carries 1.6 times 10 to the minus 19th of these coulombs. And I say how convenient because, of course, I picked this such that this 1.6 is going to cancel that 1.6. And you'd get exactly 10 to the 20th electrons that pass through. So what that means for us is that's why we get currents that are small numbers that we're used to working with, like on the single digit order of magnitude, because I'm pumping 10 to the 20th electrons through an area. Doesn't matter that they all have really, really small charges, they add up. So now let's suppose the battery is fully drained after being connected to the resistor for 1 hour. Calculate the total charge stored in the battery. So we're going to say from from full charge to zero charge takes 1 hour. So of course we have to deal with this. And this might not be something you know off the top of your head, so we'll of course show it. So we're given the special time here is 1 hour. So 1 hour is equal to, well, we know that there's 60 minutes per an hour, and then there's 60 seconds per minute. So we get that extra factor of 60. So we get 3,600 seconds. And actually, I should make this a multiply here just to show it better. So we're going to calculate the total charge stored by the battery. So there's another way to do this with ratios, but we found the current. So given the fact that we know that I is charge per time, this means that charge would be current times time. So 0.267 coulombs of charge pass through the area every second, and we do that 3,600 times. And if we do that, it's actually going to perfectly work out, and we'll actually show the ratio approach here too. Let's just type it in. Of course, you can type it into your calculator, but we said after 1 minute, 16 coulombs of charge have passed through. So after 60 minutes, which is an hour, 16 times 60 should have passed through. So what is that? Well, I am going to do that in my head. That is going to be 720 coulombs of charge. Okay. So the next circuit quantity we'll talk about, this is the most abstract. So current is pretty straightforward because it's a flow. We can sort of make some analogies with water, which we might do at some point, but current is flow. That's pretty easy to track. This concept of electric potential gives people a lot more difficulty. So we'll try to make it more reasonable here. So a battery is something we're all familiar with, but what does it do? Well, a battery separates electric charges. So we know that positive and negative charges don't like to be separated. So if you have a device that uses chemistry to force positives and negatives apart, that would take energy. And the energy required per unit charge is called this potential. So it tells you how much energy is required to separate each coulomb of charge. So what's really happening is, of course, it's not the positives that are truly moving because they're trapped in that nucleus. So really what a battery does is it has a bunch of negative charges in the low potential side and less negative charges at the high potential side. And this takes energy because these electrons are not happy that they're crammed together. So it must have taken energy to separate them. And the energy per charge is called the potential. So the more separated your charges are, the angrier the charges are going to be, which means the more energy it must cost to separate them per charge. So a certain battery has a potential difference of 9 volts across its terminal. We want to describe what this means. So we're all used to seeing batteries having voltage, but what does voltage really mean? Well, this is how much energy it would cost to separate each coulomb of charge across the battery terminals. Because a volt, 1 volt, is equal to 1 joule per coulomb. Because again, joules are energy unit. So it costs me 1 joule to separate each coulomb of charge between the terminals. So if we have a 9-volt battery, for every extra coulomb I want to separate, that costs me 9 joules. So that's cool and all, but it's still pretty abstract. So this is one of my favorite models of electric potential. We're going to do my favorite in a minute here. But I also like looking at potential as height. Because if you think about it, if you have any sort of a mass and you lift it above the ground, that costs energy. And if you were to release the mass, it will fall, converting gravitational potential energy of the system into kinetic. A similar idea will happen with electric potential energy. So we can interpret the potential as a sort of height. So if you think about this as a battery, this might be like a 5-volt battery. We could say that if a charge was fully separated all the way across the battery terminals, it would be at a height of 5 volts. And of course, this charge would not be happy that it's at a high potential. And if you released it, the positive charge would accelerate downhill. So thinking about potential as height is a useful analogy because it connects directly to gravitational potential energy and some mechanics ideas. And if you were to release this system, the positive charge would accelerate downhill. And also, an important note is just like we have freedom to choose zero height wherever we wanted when we dealt with gravitational potential energy, we also have the freedom to call zero electrical height or 0 volts wherever we want because it is a potential energy. It's a potential energy relationship. It's not exactly potential energy, but it has that same relation. Almost always, we're going to pick the 0 potential spot in a circuit to just be the negative terminal of the battery because that's the lowest height a charge could be at. So we're going to make that 0. So now let's start putting some things in a circuit. So we don't actually draw what the circuit looks like in most cases because everyone's going to draw it differently. So we've agreed to use some common symbols. So first we have a battery, which establishes a height difference between 2 points. You can almost think of this as an elevator for charges. It's given by 2 parallel lines. One of them is short to show that it's at a low height or a low potential, and the other is long to show that it's at high potential. So this does have a meaning, like the orientation does matter. This means that this is the positive end and this is the negative end. We will encounter this symbol later. This is a symbol epsilon that is going to be used interchangeably with the battery voltage because it's usually confusing if you call the battery voltage V because that's also measured in volts. So you'd get some confusion there. Is V a unit or is it a symbol? Resistor. This resists the flow of current within a wire. So this lowers the amount of current in your circuit. Think about this as if you're the kind of justification here is that if you're a person trying to walk from point A to point B, it's going to slow you down if you're going down a hallway that zigzags because you got to keep changing direction. So that's our justification as to why a resistor looks like that. Of course, we'll talk in more detail later. A special case of a resistor is a light bulb that will usually give its own special symbol too. And you can think of what a light bulb does is there's all these little junctions where the charge has to keep turning, so it's going to keep bumping into walls. And you know that during a collision, there's an energy transfer. So all these charge carriers are going to keep bumping around in the filament, causing it to get really hot, and it's going to glow. So a light bulb is really just dissipating this energy of the charge carriers. And then a switch. This is either a path that you cannot go through if it is open, no charge carriers can pass through, or if it's closed, all charge carriers can pass through. So to generate an electric current, you need there to be a potential difference between 2 points. And to do that, you have to put a potential difference between 2 ends of what is called a conductor. And this is a material in which electrons are free to move. Basically, all metals are conductors. The opposite of that would be an insulator, where even if you establish a potential difference and the charges would sort of get pushed still, there's nowhere for them to go. So an insulator does not allow charges through them. And most things like plastic would be an insulator. Now, if you establish a potential difference across a conductor, you will complete a closed loop of your circuit, which causes charge to flow. Because now we have allowed the charges to come back. Because we said a battery separates charges. So if you connect the ends of the battery like this, the electrons aren't just trapped bunched together anymore, they can start to flow around and try to restore that balance. So that's why we need a conductor, because now the charges can actually move. So this is our model of what's actually happening in a circuit. Of course, this isn't totally accurate, but this is the model we choose to use. So what's going to happen is if you connect, we know there's more electrons clustered in this negative end of the battery. So since there's more electrons crammed down here than up here, and they can't cross the gap because the battery uses chemistry to make sure nobody crosses the gap, the electrons are forced to walk around the circuit this way from the negative end to the positive end. And if they pass through any sort of light bulbs or resistors on the way there, you'll get some heat dissipation. We will assume that our batteries in this class are sort of infinite wells of charge such that they never drain. So really, this should be lowering the battery potential until you eventually drain it as the charges end up balancing. But we'll assume that our batteries have so much charge that it can just sort of pump these out forever. So a bulb will only light up if there's a potential difference across each end. Because if there wasn't a potential difference across the bulb, there'd be nothing forcing electrons through it. So we wouldn't be getting those collisions. And something we'll look at here is we're going to take this as a fact for now, that the greater the potential difference, the brighter the bulb will shine. And we'll analyze this by looking at something called electrical power later, which is the rate that the bulb dissipates energy. But we'll take this as a fact, that the bigger the potential difference across the bulb, that means the stronger the pushing force of the electron on the electrons will be. So they'll be pushed harder against the filaments if we want to justify it that way. Of course, this is not a perfect model, but this is just how we will approximate what's happening. Just trying to give some intuition there. So there's two ways primarily that we can connect two things together in a circuit. So we're defining series as there being exactly one path available between the two elements. So here we have light bulb 1. So let's say an electron goes through light bulb 1. Well, I can't just turn around, and there's no other way back to the battery, so I'm forced through the second bulb as well. So this is called a series. And a fact about series is that since there's only one path, if you somehow just break the circuit in series, nothing can flow through that series path because you've broken it. But in parallel, we actually have two different loops. So notice now, if I have an electron that's coming out of the battery, I actually get a choice. I could go through this bulb, or I could go through this bulb. And there's no problem. There's no problem here if I take out this bulb in parallel, because the electrons would just all go through the other path now. And now I'll introduce an analogy that I really like that a student came up with. And he likes to think about this as drive-throughs. So in series, this would be like a McDonald's drive-through type model where your car pulls up to the ordering lane, and you gotta wait for this lane to take your order. Then once you've gotten your order taken, you gotta go through the food pickup lane, and you get your food, and then you're out of the drive-through. So of course, it should be clear to see using this analogy why, if let's say someone's getting their food at the food window and they're arguing with the workers, essentially shutting down the lane. Well, if there's a big fight happening at the food pickup window, nobody's going to make it out of the drive-through until that issue is resolved. Whereas in parallel, this would be like a model of drive-through where you get to pick how to get your order taken. So I could get my order taken from the first worker or the second worker. Well, it's also clear to see here where if you have a disagreement happening in one of the ordering windows, that's actually not a problem overall for the drive-through. It's going to slow things down overall. But you can still go through the other window and get your order taken that way. So that's a nice way to view series in parallel, and where we actually go quite deep with this analogy. And a really special case is called a short circuit, where it's a parallel circuit except one of the parallel branches is just a wire. So what happens here is this actually does not light the bulb at all, because all of the current actually bypasses the bulb. And this is related to something called resistance, which we will talk about later. But for some intuition here, we think about resistance as being the amount of time it takes for an action to be completed in our drive-through. So let's say I'm a customer, and I come up to this junction, and I have two choices. I could go through the first lane to get my order taken, which takes some amount of time. Might not be long, maybe it's like 30 seconds, but it's still time. Or I could go through a lane that takes literally 0 time to serve me. So of course, if this is taking me some time, and this would take me 0 time, everybody is going to pick the lane that instantly serves them. So we want to break a misconception right now that says current takes the path of least resistance. That is not true. Current will preferentially split, where more current goes down the less resistive paths, but the only time you get all the current to go down the path is if you have no resistance on one of the paths. Because you can imagine, if I go back to my parallel circuit, if one of the workers, let's say this one, if this worker is fast and this worker is slow, yes, more people are going to get served by the fast lane, but if everybody went to the fast lane, it would get clogged up and people would want to go to the slow lane to counter it. So you will get current down both paths in a parallel circuit. It's just you get more of it down the fast path. But in a short circuit, one of the paths is infinitely fast. So everyone is going to pick the infinite path of just least time. So now let's draw some circuit diagrams. A circuit contains a battery, 3 bulbs in series, and a switch. So series means one path. So this means that we have one path for current. So this would be some sort of, if we want to use another analogy instead of a drive-through, we can also interpret this as traffic. So I'm trying to complete some sort of driving trip, and I want to start somewhere and come back. So we have 3 bulbs in series. So this would essentially be, we already have bulbs, so let's think of them as traffic lights. This is also how I draw my light bulbs, by the way. And usually we draw switches in the open position just to make it more readable. And that was not a great connection there. That's better. So this is a series circuit. So if we want to think about this with an analogy, we can think of this as a road where you might have to stop at a stoplight here, you might have to stop at a stoplight here, and you have to stop at a stoplight here. So notice this works as a series circuit because let's say one of the traffic lights malfunctioned and was permanently red. So if this was permanently red, no one's getting through. No one's getting through the traffic. Same thing with this switch. What if there was just if there's an open switch right here, this means that there's some sort of roadblock on this one lane road. So nobody can get through unless if the roadblock is cleared, allowing people to come through. All right, now we got a complete circuit, meaning there's no holes. Contains a battery and 2 bulbs. One bulb is always on, the other bulb is always off. So the fact that one bulb is always off, and we have a complete loop, tells us that there's some sort of shorting happening. So this bulb is shorted. So there must be some sort of a bypass happening. And given that one bulb is always on, we can probably start just by making a single closed loop like this. And if my bulb is on, I think I might give a little light symbol like that. So now we got to think about where to put the other bulb such that it's shorted. So our first reaction might be to make ourselves like the parallel highway or the double lane drive-through. And then say, okay, this guy is shorted. Well, that actually would take out this one. Because now everyone found their way through a zero resistance path. So it would be like red light, green light. So everyone's going to go through the green light. So this actually isn't the way. So what it must be is it actually must be some variation of a series where I can draw myself a bulb like this. So it would currently be on. So we just got to find a way around it. So again, why does this work? Well, think about it. This would be like we have two stoplights, but one of them, there's an alternate way. Maybe someone is like cut around through a parking lot to skip the red light. So the cars are going to say, oh, I'm not waiting for that light. I found a way around it. So they skip it, shorting the bulb. Now, when I said I do have a favorite model of electric potential, it is this one. So we'll actually visualize electric potential or height using a color map. So our rules for this is that every unique height in your circuit will have its own color. And we're going to agree that the highest potential is red, and that's going to be the potential at the positive end of the battery. I like to think of it as like a hot idea. The negative terminal of the battery is always what we're going to color blue, like for cold. So how this color model works is color remains the constant throughout a wire and stops once it hits an active circuit component. That would be a bulb, a resistor, or an open switch. And once that color hits a gap, it's going to turn around and keep exploring all the paths it can until it's hit all the barriers. So we start by spreading out the high potential color, then we'll spread out the low potential color, and then if you need anything else, you got to add some more colors. So the simplest circuits can just be red and blue, but you might get some oranges and some yellows in there as well if you have multiple steps. Usually I like to use this kind of rainbow as my potential orderings. I can't imagine a scenario that's reasonable where you'd need more than like 4. And we're going to say it is a fact that a bulb only lights up if there's a potential change, meaning a color change, across the bulb. And the greater the potential difference, color change, the brighter the bulb shines. So the brightest your bulb could be in a circuit is if you get a red to blue change, because that would be from one end of the spectrum to the other. But if you get some intermediate colors in there, it wouldn't be as bright. So we're going to say a bulb is lit if and only if there is a potential color change across its ends. So consider a simple circuit that consists of a battery, bulb, and switch in a single loop. Draw a color-coded potential diagram and justify why the light bulb is on. So this is our model. So how do we color potential? We say that the positive terminal of the battery is our high potential. And this potential explores around the circuit until it hits a component. All right, I've hit a light bulb, so I stop. Now I turn around and I explore other paths, but I don't have any other paths available. Then we do our low potential. So if we do our low potential, this also explores, and I also hit the light bulb. So notice we actually get a potential difference across the bulb. We see potential goes from red to blue across the bulb, so it is going to light up. So using our potential model, we say, if we use this like a middle school model of circuits, we might say, oh, there's a complete loop. But using our more precise model, we say there is a potential difference across the bulb. Color change. Oh, and there needs to be a switch. So we'll say this was a closed switch. So what's going to happen when the switch is open? Well, we know that if you don't have a closed switch, there's not going to be a complete loop. So let's see what's going to break this with the color model. So we know that this bulb is going to be off. So if we redo our model, except now instead of a closed switch, we have an open one, we're going to get a different potential diagram. So the question of this circuit becomes, what's the coloring going to be after this? So this time, instead of my blue being blocked blocked by the bulb, the blue is actually stopped at this open switch. So the question becomes, what do we color this portion right here? Because there is a rule that says if you run out of if the red and blue don't cut it and you have more circuit to color, in most cases you're going to add a third color. But in this case, we actually have the stipulation that there's a color change across a light bulb if and only if the bulb is lit. And we know that this bulb is going to be off. So if we look at this model, I know the argument is somewhat circular here. Just bear with me. I'm actually going to continue the red through it. So you only get a color change through lit light bulbs. So since this light bulb is not lit, there will not be a color change through it. So why is this light bulb off? Well, in this case, when the switch is open, the circuit is broken, so there's no potential difference across the bulb. Thus, the bulb remains off. Because where is the potential difference? So a better way of saying this is instead of the potential difference being across the bulb, the potential difference of the circuit is now across the switch. So the color change is across the switch, not the bulb. So I might correct that explanation a bit more and say the color change is across the switch, not the bulb. So notice that's why there's a difference. Here the red to blue is across the bulb. Here the red to blue is across the switch. The switch is closed once again, and an additional wire is added to short the bulb. So we get this. So it says draw one possible color-coded potential diagram. So there's actually two main possibilities. So we're going to do a quick copy paste here. So let's see what happens. So let's say I start exploring from my positive terminal and I hit something. So now I turn around and see if there's another path to explore. Oh, look, there is. And notice nothing has blocked me. Nothing has blocked me on this path because I have not hit a circuit component. I can also turn, I got hit by the bulb. I'm going to turn around again. Closed switches don't block me. And looks like we have a problem. Or at least not a problem, but something odd. The entire circuit has been colored one color. And I say one possible because I could have just as easily done this with blue. Tried to explore. Notice I can actually color this entire circuit blue without picking up my pencil. So both of these are equally valid. So it means the potential isn't really well defined in this circuit. Because what's happening is you're really connecting the battery to itself, so it's just going to drain. But this is why the short circuit doesn't turn on, because the entire circuit is one color. So there's no potential difference across the bulb. I don't know what the potential is. Like that, but we know it's going to be equal everywhere. So no color change. So the potential can be represented by a single color. And if it's a single color, well, there's no color change. So no brightness. So now we'll do the series and parallel analysis. So we'll go a bit faster now. So we'll begin 2 bulbs in series to a battery. Color-coded potential diagram. Okay. bulb, bulb, series. Okay, what does it mean? Well, start from our positive end. Explore, explore, explore. Oh, I've hit something. Low potential. Explore, 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 explore. I've hit something. So now we actually do bring out the third color because there will be a color change across a bulb in a complete loop. The fact that this bulb is completed, and we know that these bulbs are lit, means that there must be a third color. So often we have to use our intuition to know if a bulb is lit or not in order to determine whether there's a color change across it. So I know it's a bit of a circular argument. We have to accept knowing when a bulb will be on or not, and that allows us to unlock most of this analysis. This is a more common case. So this is going to be lit, and this is also going to be lit. And using the power of foresight, I actually used less like light markers here than I did in the past, because we're actually asked to compare the brightness of one of the bulbs in series to the brightness of a single bulb in the simple circuit, assuming this battery is the same. Justify using the potential diagrams. So notice here, this bulb steps from red to orange, then from orange to blue. Whereas in the other circuit, it actually goes entirely from red to blue. And we said that the brightness of a bulb depends on how extreme this color change is. So it's actually going to be dimmer in this circuit because instead of going directly from red to blue, we're going from an intermediate color. So in this series, there's multiple steps of potential change. It goes from red to orange-ish yellow to orangish yellow to blue. Whereas in the simple circuit, the potential was all in one step. So that's why it's going to be more dim, because we said the more extreme the color change, the brighter the bulb. And this, we have this little intermediate potential, so it's not going to be as bright. Suppose the original bulb burns out, draw an updated potential diagram for the circuit, and justify why the second bulb is also off. Okay, so we're going to try to save ourselves a little bit of time here. Can I manage to get just the color? I can. At this point, I should have just drawn the... Yeah, we're just going to redraw it. Too lazy. Too lazy. Okay. So let's say one of the bulbs burns out, which I'm going to just represent as a hole. So what is this potential diagram going to look like? Well, this is going to look similar, where it spreads out, boom, I hit something. There's a hole. You can't cross the gap. It's like an open switch. Same thing here. Hit something. But we also know that you can only change the color across the circuit components in a complete loop. And there's not a complete loop here. So once again, we see both ends are the same color. So why does the second bulb also turn off? Well, it's a similar effect. This time, the entire color change of the circuit is across a hole instead of one of the bulbs. So the burnt out bulb acts like an open switch. As a result, there's no potential difference across the second bulb because the entire potential difference of the circuit is across the hole, or the gap. So we get no lit bulb. Now let's try two bulbs in parallel. So two bulbs are connected in parallel to a battery that looks like this. So our high potential explores all possible paths, hits those boundaries, and then our low potential explores all possible paths. And now we get something that is counterintuitive to a lot of people. So a lot of people think that adding two bulbs is going to always decrease the brightness, like it did in the series case. But here, we actually get the same brightness for each. And it's the same as it was when there was just one bulb. So notice it's red to blue. And that's the only thing that determines brightness. So in the brightness is going to be the same as the simple circuit because you have made two complete loops for each bulb. So each bulb has the full red to blue across it. So in the series circuit, they had to share the drop because between the two bulbs, you had to turn from red to blue. But here, each bulb turns from red to blue separately. They're independent of each other. So now let's show what happens when one of the bulbs burns out and why this is different than the series case. Okay, so this one's easy to remove. We can just do that. And that's literally the only adjustment I have to do. So, okay, cool. There's a hole. That blocks the potential from crossing it. But there's still another route, right? There's still another route. So even though my original bulb is now whole, there's still a red to blue color change across the other bulb. So ignorant to the change, it still works. Where's my, there it is. Even though the burnt out bulb acts like an open switch, the second bulb is in its own loop. So the potential difference remains the same, causing the second bulb to remain on with the same brightness. Think about this as a drive-through lane. If it takes so long to serve a certain customer, doesn't matter if you're rerouting more customers to them, it's still that same time of service per person. And it's business as usual. If one of the lanes closed, oh well, just go through the other one. But here, if the ordering window computer breaks, nobody gets through. And now we just have a couple drawings to do. We're just saying that all bulbs are the same and the switches are closed. Okay. 3 bulbs, battery, and switch. Only one bulb is controlled by the switch. And the bulbs not controlled by the switch operate independently. So if only one bulb is controlled by the switch, that means it's independent of the other two. And the other two also are independent. So this is just a big parallel circuit. So we know that the base of this is going to be just a triple parallel. But there's no switch in this circuit yet. So we can just add a switch in any of the 3 loops. I might just put it in this first loop like there. And if we draw our potential diagram, we see the high potential is going to explore, explore, explore. And the low potential is going to explore, explore, explore. So we can see that all the bulbs are going to be lit and they're at max brightness because it's red to blue across each. But notice, as soon as I break the circuit by closing this switch, the red to blue would now be across the switch instead of the bulb in that loop and no longer operates. Circuit contains a battery and 3 bulbs. One bulb is brighter than the other 2. So there's multiple solutions to this one, as there are with most of these. This is the one I think is the simplest to come up with. So people realized that if you just wire one bulb by itself like this, this would be our maximum possible brightness. So we can just begin by creating one bulb that is going to be at maximum brightness by giving it the full red to blue drop. But now, if instead we wanted some bulbs that weren't going to be as bright, well, our way of getting different brightnesses was series, because in series, you had to share the color change to get back from red to blue. I should make these larger just to match. So if we actually add a series onto this, we see that they do eventually go from red to blue, except now it's in steps. So this is the most common solution I see that works. because notice they now just share the brightness. You can also do a case. You can also do a case where there's one bulb in front of the battery and then there's two branches, but that's harder to justify at this point. Circuit contains a battery, two bulbs, and two switches. The first switch turns the bulb on. The second switch turns the bulb off after the first switch. Okay. So it's at least easy to come up with the base for this. That's just a switch that turns the bulb on. But we actually want a second switch that turns it off. And we said that turning off bulbs in a complete loop really means that there's a short circuit involved. So we actually need a switch that's being a short circuit switch. So we can actually do this and create ourselves a short circuit. And notice if we try to potential color this, we're once again left with that case that the potential is allowed to explore actually the whole circuit, regardless if we start from red to blue, so we get a single colored circuit. So it's completely shorted. I like these. So notice we really just did qualitative stuff today. So very theoretical day. I know we did a lot with color, and there's a lot of subtlety about when does the color change across a bulb, when do I include that intermediate color, but now we get to do what we probably love and just do some plug and chug formulas after we talk about our final circuit quantity of this unit.